Hello, and welcome to this presentation on sharing trajectories with local differential privacy. This is work done by myself, Graham, and Hakan at the University of Warwick, and Divesh of AT&T. We motivate our work by noting that trajectory data is highly useful for researchers and analysts. However, existing differentially private mechanisms for doing so are restrictive and limited in their utility. As far as applications are concerned, our work can be used in societal contact tracing, as well as other urban applications, such as advertising. We contextualize our work by noting that, although trajectory sharing is well researched in the centralized DP setting, it is less well studied in the local setting, in which users perturb their own data before sharing with an aggregator. In our work, we use a distance-based LDP mechanism. Although similar LDP-inspired mechanisms are plentiful, none of these cited work satisfies strict epsilon LDP, which means they have a weaker privacy guarantee. And so to our problem, in which we model trajectories as time-ordered sequences of places of interest, with an example shown here. Our aim is to perturb these trajectories in accordance with LDP, whilst ensuring that we achieve high utility at the aggregate level. We aim to boost utility by using a range of publicly available external knowledge to influence perturbation probabilities. A tertiary aim is to develop an efficient mechanism that is scalable for real-world implementation. We now introduce the two privacy definitions that are central to our solution. Familiar to many will be the definition of local differential privacy, as shown here. In short, LDP provides a privacy guarantee to users who perturb their data before sharing it with an aggregator. Also familiar to many will be the exponential mechanism, which uses a quality or distance function to control the probability that any one response is returned. So, what information is public knowledge? Well, we deem some attributes of POIs, such as locations, opening hours, category, and popularity, as characteristics that can be used to boost utility and rule out illogical outputs. Importantly, as they are public knowledge, we do not need to add noise when using this data. We incorporate public knowledge through semantic distance functions, which relate the similarity between POIs. For example, a restaurant and a bar will have a low semantic distance, whereas a bar and a bowling alley will have a high semantic distance. Before moving on to our solutions, we introduce a final utility-enhancing constraint. To ensure illogical output trajectories are prevented, we define the notion of reachability for adjacent POIs. This ensures that an output trajectory does not have someone traveling from London to, say, Copenhagen within 20 minutes. Here, the yellow blobs are reachable from the blue blob, but the red ones are deemed unreachable. Our so-called global solution models entire trajectories as singular points in high-dimensional space. Although this may be theoretically optimal, it requires instantiating all trajectories, which quickly becomes intractable, as illustrated with this small-scale example. Although some techniques exist to speed up the exponential mechanism, we find that too much utility is sacrificed for efficiency in these cases. Hence, we move to consider an n-gram-based solution in which we perturb trajectory fragments. This helps us to preserve spatiotemporal correlations, an integral part of privately sharing trajectory data. Overlapping the n-grams helps us to preserve many correlations for each trajectory point. To ensure our mechanism is even more efficient, we partition our space by exploiting the intrinsic hierarchies that exist in our public data. This allows us to create space-time category regions, or STC regions for short. Here is a summary of our mechanism. We first translate our trajectories to the STC region level. We then perturb overlapping n-grams at the region level before reconstructing a feasible trajectory. A final post-processing step is to convert the reconstructed trajectory back to the POI level. So, how exactly do we use hierarchies? First, we can put POIs into space category regions, as illustrated here. Time can also be included. Opening hours, assumed to be public, can be utilized to allow POIs to appear and disappear as they open and close. Finally, we can merge regions to account for POI popularity, another publicly known attribute. Merging regions also provides efficiency benefits by reducing the total number of STC regions. Once we have partitioned our space, we define the set of reachable engrams. Having done so, we can now perturb overlapping engrams using the exponential mechanism, as illustrated on screen. We also perform supplementary perturbation with shorter engrams to ensure that each point is covered n times. A consequence of perturbing overlapping engrams is that each point has n POIs associated with it. Hence, we define an optimization problem to find a trajectory that minimizes the semantic distance to the perturbed engrams. Importantly, this process only uses non-private data, which means we can invoke LDP's post-processing property and not spend any of the privacy budget. Here is an illustration of the reconstruction process. We find the minimum error trajectory, illustrated here as merging colorful blobs. The output is a reconstructed trajectory on the STC region level. Note, the reachability is satisfied by the reconstructed trajectory. As a final post-processing step, we sample POIs from the STC regions of the reconstructed trajectory. This ensures the final output trajectory is in the same format as the input trajectory, that is, on the POI level. We compare our engram method to 4 other methods. The first 2 methods independently perturb POIs and time steps. IND-reach only perturbs to reachable POIs, whereas IND-no-reach allows perturbation to any POI. The next 2 methods use our engram approach. Phys-dist does not consider external knowledge, whereas engram-no-h does not use hierarchically structured engrams. We evaluate our mechanism using 3 datasets. These either use the real data directly or as the basis for semi-synthetic trajectories. You can see a summary of the dataset's characteristics here. This table shows the semantic distance between the real and perturbed trajectories in each of the 3 main dimensions. We normalize values to be between 0 and 10 and call this the normalized error. We see that engram, our method, is generally the best performing method. We can also highlight the benefit of using external knowledge, as shown here, and the benefit of using hierarchically structured engrams, as highlighted now. We now evaluate the average runtime of the mechanisms, broken down by stages. As expected, the 2 baselines that do not use optimization are very quick, although our method is the fastest n-gram-based method. Interestingly, up to 99% of the runtime for n-gram-based methods is spent using optimization to reconstruct trajectories. Better solvers or heuristics can be used if necessary. The graphs here show the change in normalized error as a number of key mechanism and dataset parameters are varied. As is evident, our solution, in green, is consistently the best performing mechanism. The poor performance of phys-dist, in yellow, further illustrates the importance of including external knowledge in perturbation. And here is how changing key parameters affect average runtime. Again, our mechanism performs well, especially when considered jointly with accuracy. In conclusion, using external knowledge and overlapping engrams in perturbation ensures trajectories can be shared locally with strong privacy guarantees and high utility. Our solution can be generalized or extended to a range of other settings, and we leave this to future work. Thank you for listening.